Assalamualaikum warahmatullahi ta'ala wabarakatuh and good evening. My name is Muhammad Hafiy bin Yusoff 25535 and today I'll be discussing the question 1B of the extended assignment. We will start with incoherency, which means a measure of similarity between waveform or traces, and incoherency can be seen in terms of amplitude, frequency and phase. Seismic wave incoherence arises from the horizontal spatial variation of both horizontal and vertical, and there are two sources of incoherence, which is the local wave scattering and wave passage effect. This is caused by the heterogeneous nature of gas field area and result in scattering, dispersion, internal multiples, mode conversion during wave propagation, true and possibility and elastic losses. And all these effects lead to significant deterioration of the seismic image in terms of amplitude attenuation and strong deterioration of the seismic velocities. This is the example from figure 1A and figure 1B from block PM311. We show incoherency. On the figure 1A, it shows a chaotic data within the gas cloud, incomplete fault structure, truncation of amplitude and frequency within the gas cloud, and inaccurate depth of the gas cloud area. And on the right, for the after process figure 1B, we can see it have a better illumination, continuity at below gas cloud, better fault structure, and strong phase and reflector amplitude can be seen. We move on to the first method to enhance the gas cloud seismic image. The first method is common focus point CFP method, which is using focusing operator, which means one-way travel time function between one point in the subsurface and all acquisition point at the surface. And the imaging of one point in the subsurface is fully described as image involve the removal of one-way travel time from each seismic source to the chosen subsurface point and the removal of one-way time from that point to receiver location. As you can see, this is a proposed gas cloud imaging workflow where based on time section, the target horizon can be identified where the vertical time will peak also be used as the apex time for the initial focusing operator for each boundary. The initial focusing operator from reflecting boundaries are calculated by generating hyperbolic operator based on these time peaks and NMO velocities. And the second one, we apply Fermat principle by combining two one-way travel time function for each source receiver combination to produce a two-way time and collect its corresponding data sample in the trace. Where for repeating this each seismic trace, it can yield an objective function based on the stack power. And if the focusing operator are correct, then the sum of all data samples along the estimated two-way time will yield a maximum. And a genetic algorithm can change the parameter of the one-way focusing operator until best set is obtained. And the third one, as a QC for the final one-way focusing operator, is corresponding to two-way travel times and can be used to flatten the short record, where the reflection event is expected at 0 time for all offset. And as for the fourth one, an interpolation algorithm is used to obtain focusing operator for each vertical apex time and each lateral focal point position, where the interpolated focusing operator represent a complete migration operator travel timetable without any knowledge about the underlying velocity model. With this densely sampled travel time timetable, a complete pre-stack image can be obtained, although the output is in the vertical one-way time. And the last proposed workflow is the focusing operator times can be used as input for tomography inversion algorithm to produce a velocity depth model, where the velocity model can be applied for depth migration or time to depth conversion of the CFP image. This is the example of CFP method, which is on the left, A, that is the Kirchhoff pre-stack time regression, and on the right, the CFP one-way time image. On the left, it uses pre-stack time regression, and it uses hyperbolic focusing operator, and on the right, CFP image use non-hyperbolic based on the estimated focusing operator. For the figure B, CFP image, the arrow shows the improvement inside and underneath the gas cloud, which can be seen clearly as this FP image directly uses the estimated focusing operator, ensuring better amplitude focusing below the subsurface complexities. And as the one-way time operator were estimated such that they optimally focus on the seismic energy, a well-focused result is obtained. Can be seen on the figure B, and the CFP image shows an improved lateral continuity on the image reflector and has a better amplitude reconstruction below the gas cloud. Next, for the second method, which is the elimination factor analysis. Elimination factor analysis is a combination of ray tracing and focal beam method to create new function of analysis. It's a combination of ray tracing method, which is rely on the number of ray hits on the reflector, and the ray should not incorporate true amplitude information. And the second one is focal beam method, which is performed quickly analysis after production of resistive model on such surface. And for focal beam, it's only provide information at specific target point, and it can be good for the gas cloud. And illumination analysis at other areas beside the target point are unknown. And for the suitability of illumination factor analysis to the area, it shows higher confidence level during survey design evaluation before starting a new acquisition, and it can compare and correlate the result from ray tracing and focal beam. This is the example of proposed illumination factor analysis workflow. The first one is before analysis, a comprehensive velocity model must be built. And at reflected depth of interest, wave is sent to surface level where the source and receiver are placed. And then the wave will converge with source and receiver before it propagate back to reflector. And after focal beam process finish, the same process is repeated for ray tracing, where for ray tracing only the wave that reflected back to the surface is considered hit. And for elimination factor, it will be calculated using mathematical manipulation from other method. The next one is the Q-migration technique, which is proposed for gas cloud. Q-migration prove improvement from derivation of kinematic and dynamic, and this is to reduce and gain amplitude loss, to have clearer structure, and to eliminate poor event continuity. Q-migration enhance lateral and vertical gradient, and to have a complete Q composition, it involves the estimation of Q and then using resultant Q volume to correct the amplitude and phase effect. The Q estimation consists of develop ray-based tomographic method and perform the analysis on depth migrated. And for resultant Q volume, it can be done in Q pre-stack depth migration and can be treat the velocity of attenuation medium as a complex number that is function of Q. This is the example of before and after Q migration process. As you can see, there is a very strong lateral and vertical gradient as well as lateral continuity on this image compared to this one before the method was applied. As you can see, it really enhance and make the amplitude becomes stronger. After that, we have the parameter suitability for each method, which is the first one for CFP. We really need one-way travel time, common midpoint stack, time section, and focusing operator for the one-way travel time. And for elimination factor analysis, we need to have velocity model, wave field extrapolation for the beam, ray implementation for ray tracing, the frequency, amplitude measure, and ray hit count. And for Q compensation, we need to have phase, amplitude, velocity model, Q estimation, and resultant Q volume to have the final model. The conclusion for this discussion, the first one for CFP, it avoid the estimation of velocity depth in early stage and finding focusing operator directly from the data via a data driver strategy. And the final image show improvement in overall resolution, reflection continuity, and recovered amplitude, which can be improved for gas cloud area. And for elimination factor analysis, it gives more accuracy on the location of the gas cloud within the subsurface, and it can have a better indication of illumination distribution of the gas cloud. And the separate outcome from the wave and ray illumination technique also confirm that individual analysis of ray tracing and focal beam might yield different conclusion compared to real seismic data evaluation. As for Q composition, it's improved seismic image below gas cloud. It can have more accurate prediction of reservoir properties, and lastly, it will be easier detection and interpretation of deeper reflector, which can be good for gas cloud analysis. And with that, I believe that is all from me. Thank you very much for listening.